Welcome to this video on binomial probability distribution. As fancy of a name as that is, we won't get into why it's called that today, but let's take a look at a particular situation. Suppose we lived somewhere where on any given day there was a 42% chance of rain. Before we start this problem, just a quick note on geography. This might be more likely, for example, on an island or some place, because at the majority of the places where you may live, rain one day increases or decreases the probability of rain the next day. So there's a connection between one day and the next. But for the sake of calculation, imagine that we're in a place where there's a 42% chance of rain every day, and that no one day would be likely to increase or decrease the probability the next day. So that each day we're in some sense a purely separate event. But we could ask the question, in any given 7-day week, how many rainy days might we have? Well, as you can see here, there could be anywhere theoretically between no rainy days and as many as 7 rainy days during a given 7-day week. And while those two extremes aren't very likely, that you'd have no rain in a week or every day having rain, they are definitely possible, and we can compute those probabilities. Before I tell you how I computed the probabilities, if I could sort of flip this thing around and tell you what I computed first and what it means. I computed the probability of no rain in a 7-day period. That probability worked out to be a little over 2%. I'll tell you how I got that later in the video. It turns out having one rainy day is more likely than none, coming in at about 11%. More on how I got these numbers later, of course. But my calculations showed that a 2-day rainy week is even more likely at about 24%. A week with 3 days of rain turns out to be 29% likely. A week with 4 days of rain is a little less likely. And so far you can see that the most likely outcome in any given 7-day week is that there'll be 3 days of rain. Again, I haven't gotten to the part where I'm telling you where these numbers come from yet. That's the very detailed calculation soon to follow. But my calculations show that a 5-day week, or a 7-day week, is 9% likely to have 5 days of rain. And the probabilities drop off as you get closer to the other extreme. There are weeks with 6 days of rain, but they only happen about 2% of the time. And at the most extreme, 7 straight days of rain only happens less than 1% of the time. Here you can see it's about 2/1000 or 0.2% likely that that's going to happen. So there are really two parts to this video. One is, how on earth did I get these numbers? And the second part is, how can we use these numbers to answer more detailed questions about rain scenarios? So first, let's concentrate on the how. And we'll start with this number here. How did I find out that in 29% of weeks, there are 3 rainy days exactly? Well, the first thing I ask myself is, what's the probability of having 3 rainy days? But that can mean a lot of different things, couldn't it? Let's take our week to go Sunday through Saturday. Sunday's the beginning of the week and Saturday's the end of the week, sort of as like a traditional calendar. When I say what are the chances of 3 days of rain, that might mean that it rained Sunday, Monday, Tuesday, and was clear the rest of the week. But it could also mean anything else, such as there was rain Sunday, Tuesday, and Friday of that week. Or maybe it means there was rain Monday, Tuesday, Thursday. Really, any combination of 3 days of the week is what's being calculated here. And you can see, just based on how many possibilities that there would be. But this is not going to be a simple calculation. So what I did, for starters, is I literally wrote out every possible 1 week long scenario here. And just to give you a few examples of what I'm talking about, look at line number 1. Line number 1 represents rain on Sunday, Monday, Tuesday, and no rain the rest of the week. Or for example, line 10, examine that and follow this logic. Line 10 represents rain on Sunday, but not Monday or Tuesday, but then rain again on Wednesday and Thursday, and none for the rest of the week. And I certainly won't read any more of these to you, but you get the idea that there really are a lot of different ways that you can have 3 rainy days in a week. There are 35 ways, in fact. And how I was able to type all these out is another matter, but there are, in fact, 35 ways that this can happen. And when we pose the question, what is the probability of 3 rainy days in a week? We're talking about all 35 of these options. More later on how I know there are 35, other than listing them. But what's worth pointing out here is that each one of these 35 lines is what we call mutually exclusive. That's fancy math for no 2 of them could happen. For example, line 14 and 15. Those can't both happen in the same week because they have rain on different days. And we're considering rain as sort of this binary condition. So as an example, as that is your example, you could convince yourself that all 35 of these outcomes are mutually exclusive. No 2 of them could happen in the same week. And the mutual exclusivity of them is important because if we want to know the probability of 3 days of rain, which also implies 4 days of non-rain, then we need to calculate the probability of each one of these 35 events in that order and add them all up together. In case you don't remember from a prior probability lesson, if you want the probability of, say, 35 mutually exclusive events, one of them happening anyways, then you simply add up the probabilities for each line. Let's take line 1, for example, and let's compute the probability specifically of that happening. And by specifically, I mean, let's compute the probability of rain Sunday, Monday, Tuesday, and no rain the next of the week, exactly in that order and precisely that scenario. Well, in order to compute that, the first thing we'll have to notice is that we have 3 days of rain followed by 4 days of no rain. And to compute that, we'll need to know that what the probability of it not raining on any given day would be. So if there's a 42% chance of rain on any single day, wouldn't that mean that there's a 58% chance of no rain? That's just 100 minus 42. By the way. So looking at the bottom of the screen, the probability of the rain and no rain falling exactly in that order, rain on Sunday, Monday, Tuesday, we could multiply all of these probabilities together and get an answer. And that answer, by the way, on my calculator, worked out to be this number. But wait, that doesn't represent the probability of any 3 days of rain. That specifically represents the probability of rain on Sunday, Monday, Tuesday, and no rain the rest of the week. But in other words, that's the probability of line 1 happening. But I have 35 things to consider here. I need to know the probability of line 2, line 3, line 4, all the way down to line 35. Now it turns out you can easily convince yourself that any one of these 35 outcomes is equally likely and has a probability of the number at the bottom of your screen, 0.008, and so on. So if I'm adding up all these probabilities because they're mutually exclusive and I want the total, I just have to add line 1 plus line 2 plus line 3 plus line 4 all the way down to line 35. And if I add up all those numbers, Shortcut, just multiply one of them by 35. But technically, if I add up all these numbers, I will get the probability of any 3 days of rain, or just having a 3-day rainy week in general. And that ends up to be the number in the table, 0.2934, that you see there in the middle. So that's where that number came from. Now, as a student, you probably wouldn't want to write out all 35 combinations. But do we really have to? Now, we don't have to write them out, but we did need to know that there were 35 of them, didn't we? Because we're adding that same number to itself 35 times. So then the interesting question is, how would I have known there were 35 combinations without writing them all out? Shortcut, combinations. If you do 7 combination 3, you'll get 35. And that tells us that there are 35 items on that list without having to make the whole list, which you can imagine how cumbersome that would be. Why combination 7, 3? Well, because think of it this way. We want to know how many ways we can have a week with 3 days of rain. And isn't that the same as saying, I have 7 days to choose from, how many ways can I choose 3 of those? And that is, by definition, the combination 7, 3, as you see here. There's many ways to compute that. Some calculators will do combinations for you and tell you that that's 35. Other ways you can use from previous lessons are factorials and so forth, and I won't go into all those details here. But suffice it to say, knowing that there are 35 combinations on that list is all we need to know without actually writing out the list. So what you can do here, shortcut, just compute the probability of rain Sunday, Monday, Tuesday specifically, or any one of the items on that list, and just multiply it by 35, which comes from the number of ways we can make a 3-day rainy week. Let's now take a look at another example where I'll illustrate essentially the same thing one more time. How did I know that there was a 9% chance of 5 days of rain in any given week? Well, the first thing I did was say, okay, 5 rainy days in a week, what could that look like? There's lots of different ways that that could be. Look at the top line on this thing here. That represents rain Sunday through Thursday and no rain Friday and Saturday. That's a good outcome for those of us who like sunny weekends. Or look at line 15, for example. Line 15 would represent rain on Sunday, no rain Monday, Tuesday, and rain the rest of the week, and so on. So these are the 21 ways I can have a 5-day rain situation within a 7-day week. Again, I'll tell you later how I knew there were 21 of them, or how you could know that without listing them. But here's the point. We could compute the probability of this first line, meaning rain Sunday through Thursday and no rain Friday and Saturday. And if we do that, which looks like this, we can simply multiply the probabilities of rain and no rain together to get that one particular outcome. Now, this particular outcome has a probability here, look at the bottom of your screen, of less than 1%. But remember, that's not the probability of having 5 days of rain. That's the probability specifically of having 5 days of rain, with those 5 days being Sunday through Thursday only. That's got a pretty small chance of happening. But that number at the bottom of the screen is not only the probability of line 1, but it's the probability of line 2, 3, 4, 5, and all the way down to line 21. So I'm just going to add the probabilities because these are mutually exclusive events. Line 1 plus line 2 plus line 3 plus line 4 all the way down to line 21. And since each line is the same, I could essentially multiply any one of those by 21 and get the answer in our probability table, the 9% approximately that you see there. Now, you probably don't want to make a list of 21 different options to know that there are 21 things. So instead, you can just do combination 7, 5. After all, the number of ways I can choose 5 rainy days in a week are combination 7, 5. In other words, how many ways can we choose 5 things from a group of 7? Most calculators will work that out and tell you that it's 21. If you have to use factorials, that's fine too, but that's where the 21 came from, and that's how you could find it without making the whole list. I'm going to look at one more example here. If you already get the point, fast forward through all this green stuff that you're about to see. But if you need to see it a third time, here goes. What is the probability of having 2 days of rain exactly in any given week? Well, first, as you might have expected, I typed out all the number of ways of getting 2 days of rain. Worth noting here that there are also 21 ways here, as there were with 5 days of rain. I'll let you think about why that may be the case. But just to give you an example, line 1 represents the scenario that there's rain on Sunday and Monday and no rain the rest of the week. Or line 14, for example. Line 14 represents rain only on Tuesday and Friday. But as you can see here, there are 21 days, 21 ways of getting no rain on 5 of the days and 2 rain on the other. So just as I did before, I computed the probability of the top line, and that's specifically rain on Sunday and Monday only. Multiplying all the probabilities of rain and no rain gives me this decimal, which is about 1%. But again, that's just the specific probability of line 1 happening. We're more interested broadly in what is the probability of any 2 days being rainy, not just Sunday and Monday specifically. So all I have to do is add the probability of line 1, line 2, line 3, line 4, all the way down to line 21, because after all, these are all mutually exclusive events. Adding up all 21 of these numbers, of course I didn't really type it in that way, I multiplied the top line by 21. But theoretically, adding up all 21 of these numbers gives me the 24% approximately that you see in your table there for 2 days of rain. If you don't want to make a list, and who does, just use combination 7, 2 to represent that there are 7 days in the week, and we want to know how many ways we can choose 2 of them to be the rainy days, and thus get the overall probability of 24% of a 2-day rain week. So that explains where the numbers in this chart came from. I didn't do all of them, but you can see how any other ones that I didn't show could also be computed using the same strategy. We call a distribution like this the binomial probability distribution. I really wish it were called the binary probability distribution because it's dealing with a binary event. And by binary, I kind of mean yes or no. Yes, it rains, or no, it doesn't on any given day. Now, of course, in real life, the condition of rain isn't purely binary. You can have sprinkling days. You can have days with total torrential downpour and everything in between. But for the purposes of our calculation, where we're considering days as either rainy or not rainy, this really represents a binary condition per day. The binomial probability distribution is the table that you see there, where we go from none of the event happening to all of the event happening. In other words, no rainy days to all rainy days within a given time period. And we can use the probability of rain on any given one day to compute this table for the whole week. Of course, the binary probability distribution isn't always used for things that have a 42% outcome. It could be any percentage or probability. And it's not, of course, only used for seven possible events, like 7 days in a row. It could be any number, but in this particular example, that's what I used. But more than likely, if you're in a mathematics course, you won't be asked just to compute the table. You'll be asked certain questions beyond the table. Well, you might be asked for a number on the table. For example, what if we were asked to find the probability of exactly 6 days of rain in a week? Well, doesn't our table show that that's slightly over 2%? So we have about a 2% chance of having 6 days of rain in any given week. So there are times when the answer to a question is one of the numbers on your binomial distribution table. But more likely you'll be asked a question, there's the answer to that one. More likely you'll be asked a question like this. Find the probability of 4 or more days of rain in any given week. If I were asked the probability of 4 or more days of rain, I would have to compute all 4 of these. You see the 0 through 3 lines? I wouldn't have to compute those. But I would have to compute all the ones on the bottom. You may see them in orange. So if I want the probability of 4 or more days of rain in a week, I'd have to compute line 4, 5, 6, and 7 here and add them up. Now I didn't show my work, but those 4 numbers at the bottom of the table do in fact add up to this. So you can see by that number that there's almost a 33% chance of 4 or more days of rain in any given week. In other words, the probability of 4 or 5 or 6 or 7 days of rain. And again, it's okay to add these because they're mutually exclusive events. If you're being asked about the chances of 4 or more days, that's essentially an or problem, 4 days or 5 days or 6 days or 7. And I'm allowed to add those probabilities because each one of those lines is mutually exclusive. By that I mean no 2 of them could happen. Makes sense, right? You couldn't have 4 rainy days and 5 rainy days in the same week. Exactly. Here's another question you might be asked. You might be asked to find the probability of 5 or fewer days of rain in any given week. Well, that would be the first 6 lines of the table, lines 0 through 5. Every one of those, top 6 lines in pink, represents the probability of 5 or fewer days of rain. And if I wanted to know the chance of 5 or fewer days, I would have to add up all those numbers in the column. Well, I added them up and they equaled approximately this. Fine, no problem, I'm done with this question. But here's something to ponder. If you look at the top 6 lines in pink of this table, realize in order to answer this question, you would have to do those 6 calculations on the right in pink. And there's nothing wrong with that, and you will get the correct answer if you do that. But suppose you didn't have this table, and you were computing this table from scratch, which more than likely you will be in most mathematics courses. Wouldn't it be easier to compute the complement of the event we're being asked about? Or the opposite, as we sometimes say in probability? Well, what's the opposite of 5 or fewer days of rain? Well, wouldn't that be what you see in green here, 6 or 7 days of rain? And if you can see the colors, the top 6 lines are pink, the bottom 2 lines are green. The probability of the pink plus the probabilities in green must add up to 100% or the number 1. So if I didn't have this table at all, let's say I had to build it from scratch, and I wanted to answer the pink question, would it not be easier then to compute the complement, i.e. the bottom 2 lines in green, add those together, and get about 2.5%, and then say to myself, if there's a 2.5% chance of a 6 or 7 day rainy week, then couldn't I, to get the pink total, without calculating any of the pink numbers, could I not just do 1 minus that complement and get the sum of the pink without finding any of the actual numbers in pink that I intimated that we may have to in the beginning? Of course, the answer to that is yes. If you didn't get the subtleties here, that's okay. You can always compute the entire table and answer the question literally. But there are some times where there's a shortcut, and I thought I'd mention that to you, as I just have. Now I'm now done with the problems, and mostly done with this video. But if I might, let me just alert you to some rephrasings of things that can be a little confusing. We just finished the question, 5 or fewer days of rain. But what if instead I had asked you the probability of less than 6 days of rain? Would you have interpreted that as the same question? It is the same question, because if you have less than 6 days of rain, that means you don't have 6 days of rain, you have less than that. But since rain on any given day is a binary condition, less than 6 is the same as 5 or fewer. Here's another phrase. Would you have recognized at most 5 days as being the same as the 2 lines above it? This isn't really a math issue here. This is more of a linguistic issue. And there are different phrasings of things in English. So if a question says at most 5, which by the way is the same as no more than 5, we mean just that, 5 or fewer. So if these 4 phrases seem obviously the same to you because of your linguistic talents and your interpretation of the English language, great. But if this seems confusing to you, you're going to want to rewind this enough times to convince yourself that all 4 of these phrases mean exactly the same thing when it comes to a whole number of days of rain in a week, which is what we're assuming here. In the same vein, a few minutes ago, we did a problem where they asked us for the probability of 4 or more days of rain. Would you have recognized that as the same as more than 3? After all, if every day is either rainy or it's not, then more than 3 days is the same as 4 or more days. This could also be rephrased, at least 4 days of rain, or no less than 4 days of rain. Again, if this makes sense to the way your brain processes language, great, you're lucky, and you would see these as the same question. If not, pause and think about it long enough to convince yourself that there are many phraseologies for any one of these questions, and be alert for those to change from one problem to the next as you go through and do these problems on your own. I want to thank you for watching this video on the binomial probability distribution, and good luck solving those problems.